Right, we're ready to get started. Our next paper is on smooth plane models for modular curves of Shimura type, and Eran Assaf is back to present.
Thank you, Kieran. Thank the organizers for being so excited for my talk yesterday that they wanted another one today. And thank you all for being here on Friday morning. More seriously, so this is a joint work with Samuele Anni and Elisa Lorenzo García, which unfortunately could not be here. So I'm presenting again. And this talk is about smooth plane models of modular curves of Shimura type. So first, I would like just to tell you what our basic setup is. So you all know what a modular curve is, but maybe the important point is that we're going to consider an arbitrary discrete subgroup of Gd2 plus R, and not just your gamma naught of n that you're used to. So our modular curves are x of gamma for an arbitrary congruent subgroup gamma, and I will denote x of gamma the modular curve, the compactified modular curve, and x naught of n the usual modular curves that you're used to working with. Okay, and the topic of this talk is models for modular curves. So maybe, oh, already a mistake. Okay, that should be 71. Just it's a reprint. But already Shimura, many years ago, found exists an algebraic curve, a smooth projective curve over Q zeta n, that its complex points are the same as x of gamma, and we call such a curve a model for x of gamma over Q zeta n. And Galbraith wrote his thesis about writing an algorithm to compute models for x naught of n. And these are over Q. Here's an example why we're interested in this stuff. So actually, you've already seen an example this week in Francois's talk, where we used models of modular curves. But maybe the most famous example is for Modularity Theorem. So in the original case over Q, we only need x of 7, but for the ring quadratic case, we already need explicit models for many more modular curves. And in the forthcoming imaginary quadratic case, even more modular curves. So we really need explicit models for all these modular curves, and sometimes they're quotients. So that's why we're interested in computing models for these curves. And we want these models because we're using some algebra geometric methods on them. And this could get complicated when our model of the curve is more complicated. So our question is, when is this model very simple? What do I mean by simple? So first of all, I want it to be a plane model, so just a plane curve, because that's where we can do the most. And I want it to be smooth. So when does a modular curve admit a smooth plane model defined over the rational? That's the question we started with. Maybe the first thing to do is to reduce it to a finite computation. So the idea is that there are only finitely many modular curves that admit a smooth plane over Q. And again, there's a question of how do you count this finitely many. So if I identify a modular curve with a congruent subgroup, then I mean finitely many conjugacy classes of such subgroups. Here's a short proof. It's not a very difficult result. So our curve is a compact Riemann surface. I'll denote by G its genus and by gamma its gonality. And our game here will be to use the genus, the gonality, and the index, which is the degree of the cover to J line. So using Yang-Yao inequality, we can bound the first eigenvalue of the compact Riemann surface using the Laplacian, as we've seen in Andre's talk in the beginning of the week. You remember there's a Laplacian, natural Laplacian on this compact Riemann surface, and we can use it to bound the first eigenvalue using the gonality. On the other hand, we have Zelberg's inequality, improved by Kim and Sarna, that gives us a lower bound on this eigenvalue. And well, conjecturally, this is a quarter, but that's enough for us. And if we assume that our curve is a smooth plane curve, then if it has degree t, the genus and the gonality have explicit formulas depending on the degree. So it's a nice game, and we just get a nice inequality on the degree. and we figure out the degree is at most 18. So the last piece that we need is that there are only finitely many congruent subgroups of each genus. So we have a finite list of genera that can appear, and for each of them, there are finitely many congruent subgroups. They're all, we can just go over all of them one by one, and then we'll be able to complete our tabulation of smooth plane models for modular curves. But as in the previous talk, as Andrew was saying, that this is a finite computation, but it's very long. So our results will not be to complete this finite computation, but just doing a first step towards it, like Andrew couldn't tabulate all the Carmichael numbers. So how do we do that? So first of all, I will talk a little bit about producing models at all, not only smooth plane models, but models for modular curves. So the most methods that work for our setting produce canonical models. So I'll tell you what a canonical model is. There's a theorem due to three that if we have a smooth projective curve of genus larger than 1 that is not hyperelliptic, then the canonical divisor, just the holomorphic differentials, give us an embedding into projective space. Nether later gave a more explicit theorem that actually shows that the ideal defining this image is generated by elements of degree 2, except in some cases where you need an extra element of degree 3. These are cases either of genus 3 and 6, where the curve is smooth plane curve, or when the curve is trigonal. So using this theorem and by computing modular forms, there are recent algorithms due to Box or Zerina that compute models for the canonical models of a modular curve. And there are some technical conditions that I will not go into, but there is an algorithm to compute a canonical model over Q for such modular curves. So here G is a subgroup of Gd2 mod NZ, but you can intersect it with SL2 and pull back to SL2Z, and you obtain modular curve X gamma like we had before. Okay, so now we have models for, we have algorithms to compute models for modular curves, but there's a problem. These algorithms have long running time. Although it's polynomial in n, the exponent is very large, and it's not right now it's not possible to compute all of them, even for low genus such as 6. So there are two ways to get around this. One is just compute what we can. So we did that, computed everything that we can using these algorithms. But another one is to restrict to a family, which is easier to compute. So something that is slightly larger than x naught of n, which is already known, but is not everything, and we can compute it more easily. And that's the reason to introduce groups of Shimura type. So we call them of Shimura type because Shimura was the first to introduce them. But these are just groups of the following form. So these are subgroups of gamma naught of n, where the diagonal is a subgroup of the multiplicative subgroup, and the upper right corner is also a subgroup of C mod n. So we call these congruent subgroups of Shimura type, and for these we can readily compute models, the canonical models for the modular curves. But wait, I told you I'm interested in smooth plane models. Now I only have canonical models. What do I do? So let's talk a little bit about smooth plane models. For small degree, that's easy. When the genus is either 0 or 1, you can always find a smooth plane model. When the degree is 4, G is 3, so we can get either a hyperelliptic curve or a smooth plane quartic, which is the canonical model. So computing the canonical model is just a smooth plane model in this case. When the degree is 5, we can only have two cases. So either the canonical ideal is generated by degree 2 elements by Nether-Petry's theorem from before, and then we have a smooth plane kintic. So either we have a hyperelliptic curve or we have a smooth plane kintic where we have degree 2 elements and one degree 3 element in our ideal. So the degree 2 elements give us a P2, and the parameterization we can use to find the smooth plane model. So just parameterize the degree 3 generator. More generally, what we're looking for is what is called the Gd2 linear series. So we're looking for a linear series which has degree D and embeds us into P2. You can think about it as a line bundle which has global sections of dimension 3. And this is a very well-known problem in real nether theory. And if we write SC for the coordinate ring of the canonical model, then we can consider the minimal free resolution of this ring. And a slight refinement of Nether's theorem that I cited before tells us not only that F1 over there is generated by degrees 2 and 3, but it actually tells us that each of these components in the minimal free resolution is generated only in 2 degrees, I+1 and I+2. And the number of generators of each degree is called the graded Betty number. So we'll denote these by beta ij. And what Nether's theorem is saying is basically that they're all 0 unless j is I+1 or I+2. So far, we only looked at the case I=1, but when we go to higher genre, we can use the graded Betty numbers of larger i's. And we make use of the following theorem by Mark Green, that if C is a smooth curve and it has a Gd2 linear series, then the corresponding graded Betty number is non-zero. Okay, great. So now, if we want to show that the curve doesn't have a smooth plane model, then it's quite straightforward. We just compute the canonical model. We build the minimal free resolution. We compute the graded Betty number. And if it's 0, we know that it can't have a Gd2 linear series, so we can't embed it. We can't embed it smoothly into P2. Seems like we're done. So not quite. First of all, we need to be able to go over all congruent subgroups of a given genre. Even though this number is finite, they're only tabulated for a genus up to 24, which already restricts us only up to degree 8. But that's okay, we can go up to degree 8. So I would like to say that our main result shows that there is no modular curve of Shimura type which admits a smooth plane model of degree up to 8. But that's also not true. There are 4 exceptions for which we couldn't prove our theorem. We're still working on it, but we are able to show that for degree up to 7, there is no modular curve of Shimura type with a smooth plane model. And if it is of degree 8, then it must be one of these 4 curves up to a twist. Okay. So how does the proof go? Basically, what I just said works only for degrees 5 and 6. So for degree 5, we have a canonical model generated by quadrics. And for degree 6, all but one curve have the graded Betty number equals 0. This one curve is x0 of 92, which is a double cover of an elliptic curve. So it also can't have a smooth plane model. But when you go to higher degrees, we need some more tools. Basically, this computation of the graded Betty numbers is also very difficult and also takes a long time. So what we're using is Aitken-Lehner involution. I will not go through the definition of what an Aitken-Lehner involution is. The point is that there's a natural involution on modular curves, and one can use it in the sense that if we have a smooth plane curve, we can study all the possible involutions on a smooth plane curve. And that was actually done. And an involution on a smooth plane curve of degree D, we can count its fixed points, we can find the gonality of the quotient, and we can use this information in our research. So how exactly does it work? That's how we finish the proof. So for degrees 7 and 8, we can look at the Aitken-Lehner quotient. For example, if degree is 7, then we find that all but 6 of the curves are degree 4 covers of a hyperelliptic 18-linear quotient. And this means we have a degree 8 map to P1, and that can't happen for a degree 7 smooth plane curve. So that's how we finish the work for all but these 6 curves. For the remaining, we can use Riemann Orbits that gives us information relating the genre of the 2 curves and the number of fixed points. So we can compute from the genus of the curve and from the number of fixed points of an involution, we can compute what should be the genus of the 18-linear involution. And so all we have to do is find some 18-linear involution such that the quotient has a different genus. This method also works for d equals 8 for all but 5 curves. We said before that we have 4 exceptional curves, so what's going on here? So we can use, after we compute the quotient, even if it has the correct genus, we can compute the graded Betti numbers of this quotient. And this helps us to rule out also the case of x0 256. As a final note, I would introduce something that came up during this research, which is quite interesting in my opinion, and that's a trigonal modular curve. So as I said before, we didn't just compute models for groups of Shimura type, we also computed models for groups that are not of Shimura type as much as we could. And among the curves of genus 6, we found one canonical model which is not generated by quadrates. So this label here is the label in Cummings and Pauli database. And this yields the following modular curve that has a nice equation, trigonal superelliptic curve, and it was very surprising to find such a curve. Thank you.
Some questions?
What do you use for computing graded Betti numbers?
So there are several.
Could you repeat the question?
Yeah, sorry. So he was asking, what do I use to compute the graded Betti numbers? So there are well-known algorithms that are implemented in both Magma and Macaulay to compute graded Betti numbers, and we just use these. Yeah.
I guess I have a question. Maybe I don't need to repeat it. Say you, instead of looking for smooth plane models, you were willing to accept, something that's smooth except for one node, except for 2 nodes, some fixed number of nodes. How much of this whole process would carry over? That question.
I guess most of it.
Does the green inequality do something like this still? That right? Do you still have a criterion in terms of that graded ring for it's a plane curve up to singularities of some fixed multiplicity?
Yes. I guess it's a bit complicated. So I think we only know results completely for G equals 6. And some of these are only conjectural for higher genre. So this is related to Green's conjecture. I haven't talked about it here, but this is not just a one direction theorem. This is the easy part of a larger conjecture. But I mean, given the generators, if you already compute the minimal free resolution, then you can really try to reconstruct the embedding of your curve and then hopefully obtain this nice model if you have it.
All right, because this nice model is going to be unique once the genus is gone.
I have a question. Are you willing to conjecture that there are no modular curves with the smooth plane model of genus 4? Do you think they're there or not?
I don't think they're there. I think it's highly unreasonable
These curves, especially these that correspond to group status Shimura type, they parameterize something interesting.
Oh, yeah. So all these curves parameterize, you can think of them as modular space, parameterizing elliptic curves such that the image of the Galois representation lies in a certain subgroup. I mean, the image of the Galois representation on the torsion points of order n, where n is the level of the concurrent subgroup.
See any further questions? So let's go on again.